Have you ever wondered how your computer handles complex mathematical operations? It all began with the invention of math coprocessors. Imagine the birth of a device so revolutionary that it would forever change the way computers performed calculations. This was the dawn of the math coprocessor. A specialized piece of hardware, the math coprocessor was designed with a singular purpose: to handle mathematical operations, particularly the tricky and intricate world of floating-point arithmetic. In the early days of computers, the Central Processing Unit, or CPU, was tasked with all aspects of a computer's operations, including mathematical computations. But as the need for more complex computations grew, so did the need for a more efficient way to handle them. Enter the math coprocessor. These standalone chips, like the Intel 8087, were designed to work in tandem with the CPU. They were added to computer systems to enhance their capabilities, specifically in the realm of mathematical computations. These early math coprocessors were a marvel of their time, enabling computers to perform complex calculations that were previously thought to be out of reach. They were particularly adept at handling floating-point arithmetic. This involves operations with real numbers, those that have fractional parts. Without the math coprocessor, these calculations would have been slower and less precise. But with it, computers were able to execute these operations with a speed and accuracy that was nothing short of revolutionary. These early math coprocessors were not without their quirks, however. They were separate chips that needed to be added to the system, which could be a complex and daunting task. But despite these challenges, they laid the groundwork for the advancements in CPU architecture that we see today. The invention of math coprocessors was a significant step forward in computing, enabling machines to handle complex mathematical computations with ease. As we continue our journey through the evolution of math coprocessors, we'll see how they have become an integral part of modern computing, enhancing not just the speed, but also the precision and versatility of our beloved machines. The primary function of a math coprocessor is to accelerate mathematical calculations, particularly those involving real numbers and decimal fractions. Let's delve a little deeper. Picture the Central Processing Unit, or CPU, as the brain of your computer. It's responsible for executing the instructions of a computer program. But when it comes to crunching numbers, especially those pesky fractions, the CPU might find itself in a bit of a pickle. That's where the math coprocessor swoops in to save the day. A math coprocessor is like the trusty sidekick to the CPU. It extends the CPU's capabilities by taking over the heavy lifting of mathematical computations. This dynamic duo allows your computer to perform operations like addition, subtraction, multiplication, and division at lightning speed. But the real magic happens when we dive into the realm of floating-point arithmetic. Now, floating-point arithmetic is all about dealing with real numbers, the ones with fractional parts. You know, those numbers that don't play nice and fit neatly into whole integers. And this is where our math coprocessor truly shines. It's designed to handle these complex calculations with a level of precision and speed that leaves software-based approaches in the dust. But what does this all mean in practice? Imagine you're working on a graphics-intensive project or running a scientific simulation. These tasks involve a colossal amount of number crunching. With a math coprocessor, these calculations are performed swiftly and accurately, allowing your project to run smoothly and efficiently. In essence, a math coprocessor is like a super-powered calculator tucked away inside your computer. It works in harmony with the CPU, tackling the most complex calculations and freeing up the CPU to focus on executing other tasks. With the advent of math coprocessors, computers could perform complex calculations faster and with higher precision. So the next time you're breezing through a computation-heavy task, spare a thought for the humble math coprocessor, working tirelessly behind the scenes. Like any other technology, math coprocessors adhere to certain standards and have seen significant integration over the years. To ensure uniformity and accuracy in floating-point arithmetic operations, many math coprocessors stick to a well-established standard called IEEE 754. This standard is instrumental in defining formats for representing real numbers, along with rules for arithmetic operations and rounding procedures. So why is this important? Well, by adhering to this standard, math coprocessors can deliver consistent results across different platforms and applications. It's like having a universal language for all math coprocessors to communicate and deliver accurate calculations. Now let's shift gears and talk about integration. If you've been following along, you might remember that in the early days of computing, CPUs and math coprocessors were separate entities. You'd have the CPU doing its thing, and then if you needed a bit more mathematical oomph, you'd add a math coprocessor to your system. It was a bit like having a sidekick dedicated to handling all the number crunching. However, as technology evolved, this separate sidekick started to seem a bit redundant. Why have two chips doing different tasks when you could have one chip that does it all? And so, modern CPUs began to integrate the functionality of a math coprocessor directly into the processor architecture. This shift not only made systems more efficient, but also reduced the cost and complexity of computer design. We've come a long way from the days of separate math coprocessors. Today, the functionality of a math coprocessor is typically baked right into the CPU, forming an integral part of the processor architecture. This integration has streamlined the computational process, allowing computers to perform complex mathematical operations faster and more efficiently. So, the next time you're marveling at the speed of your computer or the stunning graphics in your favorite video game, take a moment to appreciate the humble math coprocessor. It might be hidden away inside your CPU, but its impact is anything but small. This integration has streamlined processing and improved the overall performance of our computers. Math coprocessors significantly improve the performance of applications involving complex mathematical computations. This is more than just a statement. It's a testament to the transformative power of technology in our daily lives. Consider the realm of scientific computing. Here, mathematical models of physical phenomena are built, tested, and refined. These models can involve equations that are highly intricate, requiring substantial computational power to solve. Enter the math coprocessor, a silent yet powerful ally that tirelessly crunches numbers to bring these models to life. With a math coprocessor at the helm, calculations are executed faster and more accurately, bringing us ever closer to the truths of our universe. Similarly, in engineering simulations, math coprocessors prove to be indispensable. Whether it's a civil engineer designing a bridge, an electrical engineer developing a circuit, or a mechanical engineer perfecting a machine, they all rely on math coprocessors. By offloading complex calculations, these specialized chips allow engineers to focus on the creative and innovative aspects of their work, pushing the boundaries of what's possible. Now, let's shift gears to graphics rendering. When you're marveling at the stunning visuals of the latest blockbuster, or getting lost in the immersive world of a video game, you're experiencing the magic of math coprocessors. They handle the hefty calculations needed to create realistic lighting, shadows, textures, and movements, bringing virtual worlds breathtakingly close to reality. But the influence of math coprocessors doesn't stop there. They're also the unsung heroes of multimedia applications like image and video processing. Each time you apply a filter to a photo, stream a video, or even take a video call, math coprocessors are hard at work behind the scenes. They swiftly handle the mathematical operations needed to process, compress, and decompress digital media, ensuring you enjoy a seamless and high-quality multimedia experience. So, you see, math coprocessors are everywhere, silently enhancing our technological experiences. Whether it's rendering a high-definition video or running a scientific simulation, math coprocessors play a critical role. They are the invisible powerhouses driving the digital world, tirelessly working to make our virtual experiences faster, smoother, and more realistic. In modern computing, math coprocessors have found a new home in the form of graphics processing units or GPUs. These powerhouses of computation are often used as potent math coprocessors, demonstrating their immense capability to handle large-scale mathematical operations. The GPU's strength lies in its ability to excel at parallel processing, a method that involves carrying out multiple calculations simultaneously. This makes them invaluable not just in their traditional role of graphics rendering, but also in general-purpose computing tasks. Imagine a bustling city where each citizen is a math coprocessor, working together in parallel to build a complex structure. This is the world of GPUs. Their ability to handle multiple tasks at once makes them well suited to dealing with the heavy lifting of mathematical operations, speeding up processes, and enhancing the overall performance of a system. But these math coprocessor capabilities of GPUs do not magically manifest themselves. They require the explicit instruction of software developers. Developers need to write code that leverages these capabilities, essentially giving the command for the GPU to step into its role as a math coprocessor. This is where programming languages and libraries with support for SIMD or single instruction, multiple data instructions come into play. Intel's SSE or streaming SIMD extensions and ARM Neon are examples of such tools that can efficiently utilize math coprocessors. The journey of math coprocessors from standalone chips to integrated parts of our CPUs and now GPUs is a testament to the evolution of computing. With each passing year, they continue to become more sophisticated, more integrated, and more essential to our computing systems. They are no longer an optional add-on, but a fundamental part of the architecture that drives our digital world. From standalone chips to integrated parts of our CPUs and GPUs, math coprocessors have come a long way, continually enhancing our computing capabilities.